Okay, hello, this is Jackie from Cyber Systems, and today I'm going to establish a test and verification environment for vehicle controllers with model-based design approach. Let's take a look on today's agenda. This is the agenda for today's speaking, and I'm going to split the talking to 4 parts. First, I'm going to show you the vehicle modeling by CarSim. We'll learn what is CarSim and how Cyber Systems help customers build their own vehicle model. 2 techniques will be shared in this part. The next part will be the introduction of the requirement we receive from our customer in autonomous vehicle and ADAS. Although we don't have a lot of global vehicle OEM in South Asia, we do have lots of Tier 1 and Tier 2 suppliers. In the same time, lots of research institutes are our major customers. They have some requests based on autonomous vehicle and ADAS, including advanced camera sensor, LiDAR sensor, and the big-scale traffic flow simulator. We will reveal the details in this section. The third part will be the introduction of an open-source simulator, CarSim. CarSim is a simulator for development, training, and validation of autonomous driving system. Unreal Engine is used to build up CarSim as a virtual reality AV testing system. Based on Linux, CarSim could be integrated directly to users' control environment, such as AutoWare or Apollo. Lots of flexible API and the C++ environment make CarSim being famous with developers. The last part is the autonomous vehicle testing system by CarSim and CarSim. We've integrated CarSim with CarSim and even with AutoWare. This kind of total solution helps our customers build up their target vehicle model in CarSim and test with their control algorithm. We will see more details in this section. So, let's start from section 1, vehicle modeling by CarSim. Before we start this topic, I would like to ask you why we need simulation. Vehicle Testing Institute have started testing and validation from almost 60 years or more. From Europe to America, all the testers face a serious fact. Vehicle testing is dangerous and expensive. As you can see, if you crash this truck in real world, you might spend over $150,000 US, not include the test driver and the crew. Therefore, the requirement is coming. We can't afford this kind of expense, but testing is important to evaluate our vehicle's performance. Can we do some simulation before real testing? That is the reason why we need model-based design. Model-based design is a method. This method is used in controller development and testing, which is based on the response of planned model. It also be used in various kinds of industrial fields, such as aircraft, power grid, vehicle, battery, and so on. Model-based design is useful for product evaluations, system integration planning, controller designing, and development. We can say that everything in the world can be a plane model. Now, we have a new name, plane model. And I will explain you what is plane model in the next slide. So, what is the plane model? I could assume that everyone here knows that force equals to mass multiplied acceleration. If I put a force on a mass body, it will have a specified acceleration. That mass body is our controlled plane model. We can say that if the model is accurate enough, we can know the acceleration value in any time. We can develop a controller to control the acceleration value based on the math equation. Let's make the problem more complicated. The F equals to NA is not how the real world works. The real world is more complicated. We have friction, damping, and other mechanical parts. However, if our background knowledge is strong enough, we can still make the plane model as a transfer function, or you can say state space function. For example, force is equals to nx double dot plus bx dot plus kx. You can get the transfer function by Laplace transform, and this transfer function is going to be used when we want to develop a controller for it. The question is, we have to know the condition very well in order to build up the model. Okay, let's summarize what we have known now. We introduce the concept of model. A model is a digital twin from a real target. It will respond as a real object. A model is built via our domain knowledge. If we want the model response more like the real one, we have to consider more details. A model should act as the real target. Therefore, we can develop our control algorithm. A model should feedback signal we want. It means that the model should have the details. For example, if we want to know how much force should I use to make the mass body move with 1g acceleration and 0.8 friction, I must include the friction parameter in my model. In conclusion, development based on the model is called model-based design. Okay, after we learned about the model and the model-based design, I'm going to show you about the vehicle modeling. We've learned about model and the model-based design. And the most important thing in modeling is the domain knowledge. So how about the vehicle model for model-based design? In vehicle dynamic modeling, we will probably use some simple model, for example, 2 degree of freedom vehicle model, 3 DOF vehicle model, and a multi-DOF vehicle model. The 2 DOF vehicle model is a simple vehicle model, linear and ideal. The only variables are the lateral speed and the yaw rate. You might find some papers build control algorithm based on 2 DOF vehicle model. Keywords like direct yaw moment control, chassis control, four-wheel steering can help you find this model. This model is good, but not good enough. Let's take a look on 3 DOF model. This is the 3 DOF vehicle model. It is better because we have the longitudinal speed. We can have some powertrain controller on it. However, it is still ideal. We don't have some suspension details in this model. Although it becomes nonlinear, it is not the model we want in the end. So the goal is much farther than we can imagine. We have to think about the suspension system, the brake system, and the steering wheel system. If you haven't get lost here, we still have tire model, suspension kinematic and compliance, and aerodynamic. There are lots of details in vehicle model that can be easily put into the multi-DOF vehicle model. More detail means more simulation time with lots of nonlinear parameters. In the same time, more details means you have to completely know about a vehicle. That is the hardest part. Lots of people will say that this vehicle model is too complicated for me, except for the specified model. However, we can still say that if your background knowledge is strong enough, you can build your model in this way. In the next slide, I will show you a different modeling method. The modeling method I have shown you before is based on math function and pure calculation. It is fast, but the accuracy depends on the completeness of the model. If our domain knowledge is not strong enough, we would probably get a non-accurate model. This method is usually used in system-level design. The other modeling technique is finite element modeling, which is using CAE simulation tool. The idea is separating the model to finite meshes and simulation each mesh's response. CAE simulation can have a higher accuracy. However, the trade-off is simulation time. Generally, we will spend tons of time to simulate one part of vehicle. We will probably use this method when highly nonlinear part in the system is concerned. Let me use a graph to explain this for you. In this graph, the x-axis is the simulation time and the y-axis is the simulation accuracy. We have 2DOF and the 3DOF model, which is fast but not accurate enough. The multi-DOF is accurate, but we have to spend more simulation time. And the CAE simulation is the most accurate technique with lots of simulation time. We can also find that the relationship between simulation time and accuracy is not linear. One little improvement in accuracy might cost 10 times of simulation time increasing. The question is there any method that can simulate with high accuracy and short simulation time? The answer is yes. The answer for accuracy and time is modeling by lookup table. The lookup table is built by experiment and simulation result. They help us to implement nonlinear and complicated model. And this kind of model is also called black box model. As you can see, we can build an engine model by table. The table will determine that how many torque the engine would output at current throttle position and engine speed. In this table, we do not concern about the design of engine, the volume of engine, or the architecture of the engine. All we want to know is the performance of the engine. With this model, we can have a higher accuracy with short simulation time. Only question here is we have to build a complete architecture of the plane model first. We need domain knowledge. However, some simulation tool can help us to conquer this problem. CarSim is one of the simulation tools that can solve the problem. It has model architecture from chassis, powertrain, brake, steer, suspension, tire, and aerodynamic. All we have to do is import the parameter of our target vehicle to CarSim to build the model. Also, user can use CarSim to build testing procedure and environment. You can design your own testing sequence in CarSim with your vehicle model. Now, we know about the vehicle model well. The next slide, I will use an example to help you understand about the system level and the component level. We take the transmission as an example. Assume that we are a transmission engineer. We will probably concerned about the cost, the volume of transmission box, the heat transfer efficiency, the durability, and the power efficiency. you will find that the performance of the transmission is the main object. However, if we are vehicle controller engineer, we will think about how can we get the gear state signal. Can I implement my shifting schedule? How could I receive the fault or warning signal? So you will find that the whole vehicle performance is the main object we concerned. Here is a comparison between system level and the component level. For transmission engineer, the object is component level development. The tools for component level design need to have accurate simulation result for complicated conditions. CAE tools like ANSYS Mechanical is suggested. However, for vehicle controller engineer, the object is system level design. The tools for system level design need to have the whole dynamic of plane model. The behavior of target is much important than the details. Simulation tools like CarSim and TruckSim is suggested. We could find that we select different simulation tool because the requirement is different. After we modeling the vehicle, we will have to do some calibration to make sure the model works as the real vehicle. There are a lot of calibration we can do. Generally, we use vehicle dynamic testing method. The method is used to check vehicle's spec and performance. It means that we can easily understand whether the vehicle model is accurate enough. We can also evaluate vehicle performance by the result of testing. Most of the testing sequence is open-loop control testing. Open-loop means we control the car without any kind of vehicle dynamics feedback. For example, full throttle instead of constant speed. Turn the steering wheel with constant force instead of specified angle. Full brake no matter ABS is on or off. It will prevent the response error from human control. Common vehicle dynamic tests include constant radius, frequency swept steer, step steer, impulse steer, on-center steering, straight line braking acceleration, and braking in turn. This kind of testing will help us know about the vehicle performance well. In this slide, I will use a user case to show you how CarSim finds problem for your design. In this case, the user used a unique steer system like recircular steering system. And this animation shows a recircular steering system. The customer actually used a multi-link arm to control the steering angle. And the relationship between steering angle to pinion arm angle is like this graph as a result of the multi-link arm. You can see that the relationship between steering angle and pinion angle is highly nonlinear. And we hope then to build it in CarSim and see what will happen. After modeling, we test this vehicle with the vehicle dynamic testing static steer test with brake arm. The procedure is that vehicle is static with brake arm, and we will rotate the steering wheel smoothly. Brake arm will make sure that the vehicle will be static in the longitudinal axis so that the torque in z-axis will have a bigger impact. You can see from this graph, the x-axis is the steering angle and the y-axis is the steering torque. The key point is the slope between steering torque and the steering angle. In vehicle dynamic theory, We call it steering gradient. The steering gradient will show whether the steering wheel is good to drive. As you can see, we have lots of rapid increasing or decreasing in steering gradient. This makes the vehicle hard to drive. For customer who is starting autonomous vehicle controller, this helps them find the problem. They knew that the steering system is very hard to control for their controller, but they never found that the problem is coming from the bad steering system design. We help users compare to real target and find this problem, improve it and solve it. Help them reduce the time in the end. Another case is Pirelli. Pirelli use CarSim to test about their new tire model. There are two testing procedures: same distance to compare the fuel consumed, same throttle command to compare the travel distance. We can imagine that if we want to test this in real world, we need two teams to maintain the vehicle condition, doing their best to make sure that the vehicle shows no difference in spec of tires. At the same time, these two vehicles will always have some difference. For example, the engine will have difference since that the mileage is different. The testing environment cannot be always the same. Sunny, rainy, dry, or wet can have impact for the testing result. All of these variables can be controlled in simulation. We can have a totally same vehicle except for tires in CarSim. The simulation differences are as a fully result of the tire model's difference. They use CarSim to save lots of human costs and vehicle maintenance. Simulation tool can not only help you modeling and calibration your vehicle, but also help the controller design. Vehicle can be controlled by driver, controller, or both. We can use simulation tool to build different testing procedures, run simulations with driver controller, and lots of testing environment. This slide shows some vehicle control function example. As you can see, vehicle control function should get some information from vehicle, such as vehicle speed, wheel speed, and yaw rate. If you want to develop the controller, simulation tool should feedback these kind of variables to test your control algorithm. For example, ABS controller will calculate the brake command via the value of current vehicle speed and fuel speed. As an example, the testing of anti-lock braking system. We can overlap two kinds of simulation results, with or without ABS controller on split friction road. Test and compare with different kinds of model will be easier and cheaper in simulation. We can use these to develop and tuning our controller with very low cost. This is how we build vehicle model and develop controller with simulation tools. Much quicker and much safer. And there are lots of techniques we could use in vehicle model validation and verification. We have mentioned in previous slides that we can drive on the road, get some data, compare to simulation result, and tune the vehicle model to our goal. However, the most efficiency method to build up the vehicle model is by kinematic and compliance test, which is known as KNC testing. The story is we help customers to do the KNC testing and import the result data to CarSim. Although KNC testing can represent the characteristic of chassis, we still need to rebuild either static or dynamic testing to validate the vehicle model in details. Let's take a look about what is KNC testing. This video shows a classical kinematic and compliance testing. As you can see, KNC testing is going to acquire vehicle's chassis parameter. To say it more precisely, the chassis feedback includes the steering system, tire system, suspension system, and the chassis itself. A KNC testing is going to figure out the details. The final goal is we have to make sure the relationship between tire and the ground and reproduce it in every step of our simulation. The next slide will help you understand more about the KNC testing. To understand the KNC testing, the question would be, what can we have from KNC testing? The KNC testing can give us our target vehicle's chassis behavior. The result of KNC testing is a series of tables. For example, this video shows a multi-link suspension system. As you can see, when the suspension system is compressing or relaxing, the wheels are moving. Since that our suspension system will never be vertical to ground. Every time we compress or relax the suspension system will cause the tire move in longitudinal and lateral direction. As a result, the contact point between ground and the tire is changed. The direction of resistance force from suspension system is changed. The direction of resistance force from ground is changed. Basically, everything is changed. So that it's very important to have the chassis KNC testing to know that whether this chassis is good or not. In CarSim, we can rebuild the same testing scenario of KNC testing. As this video, we rebuild the KNC rolling testing in CarSim. Generally speaking, what we are doing is to validate every detail between real car and CarSim's car. This kind of testing can help us make sure the differences between the two models. I also played this video 8 times faster, since that when we are doing kinematic and compliance testing, the testing time will be very long to reduce the transient response. After KNC testing, we could have an almost 99% plus vehicle model. However, there were some cases we couldn't use KNC testing. Sometimes, our customers have problems in getting KNC testing. The probable reason would be they are not OEM. They don't have the budget to do the KNC testing, or they just a supplier of specified subsystem. They don't even have a car. This kind of situation is always happened in Southeast Asia. For this kind of customer, we also develop some techniques to help them. The most effective one is tuning the CarSim model with Optimus. I'm not going to reveal the details of Optimus and how do we do that in today's presentation. However, for your information, we could tune the vehicle model in about 1,000 times automatic simulations, 100 minutes simulation time in total, and very close result for one testing scenario. Our customers are satisfied with the result. They don't need to pay for the KNC testing to get this kind of parameters. Both KNC testing and optimization by Optimus are all solutions to do the vehicle modeling V&V. So let's summarize what we have learned in previous slides. First, I've shown you that CarSim have an accurate vehicle model architecture, including powertrain, chassis, steering, brake, and tires. The most important of this subsystem is chassis. So the second one is we have to do the V&V between simulation and the real vehicle. The feedback from simulation model should be as accurate as possible. In order to do that, K&C testing is introduced to you. We could use K&C testing to have a full vehicle chassis model. For a customer who don't have the vehicle and who don't have enough budget, Optimus is used to build and tune their vehicle model. Let's say that we have known about the importance of vehicle model and how to do that. And the next part of the presentation will be the requirement from autonomous vehicle and ADAS. Okay, the requirement from autonomous vehicle and the ADAS is more than vehicle dynamic model. Not only vehicle simulation, but also every scale vehicle is asked by our customer. Since that there are a lot of business modes of autonomous vehicle, our customer asks from passenger car to touring bus, autonomous mobile robot to big truck with trailer. For this kind of requirement, CarSim and TruckSim are introduced to them. However, the question is not that easy. For autonomous vehicle, more and more high-end sensors are requested. If we back to 20 years ago, a car with radar is a fashion design. We probably got shocked when the warning signal showed in parking. However, if we sell a car without Level 2 Plus ADAS system, the car will probably be rejected by our customer. Modern cars have to equip lots of sensors, such as front camera and radar, surround view parking assistance system, full function of ACC, AEB, and every fashion AV ADAS device and function you can imagine. Basically, this kind of function are built by three kinds of sensors: radar, LiDAR, and the camera. What we have to do is modeling and simulation. The third part is the environment and the scene. We are using more and more high-resolution camera. The virtual environment should have more and more real environment and the scene. The requirement is from characteristic to real rendering. The fourth part is traffic simulation. We have to reproduce every situation from real world to simulation. The last part is localized elements. We help customers build a localized environment like lane marking and traffic signals. Let's start from the vehicle dynamic modeling and the simulation. Just like I have mentioned in previous slides, we use CarSim and TruckSim to do the vehicle simulation. The most important thing is that only with vehicle dynamic modeling and simulation, we can have the response of vehicle on different road surface and friction. Our customer in autonomous vehicle or ADAS usually use it for three application fields: controller testing, driver in the loop testing, and the comfort of AV ADAS. I think we can all understand about controller testing and the driver in the loop testing. Let's talk more about the comfort of AV ADAS. The story is not only AV ADAS function, but also the comfort our customer want to test. No one wants to sit in an autonomous vehicle which will always make you sick, make you uncomfortable and want to leave the car. The comfort of an AV ADAS vehicle is also important. Since we have talked lots about vehicle modeling, now we should go to the sensor simulation part. There are three major kinds of sensor our customer want to use: camera, LiDAR, and radar. Customer use camera to do the perception and the decision testing. And perception means the ability to see, hear, or become aware of something through the sense. In AV ADAS, perception means the ability the controller can sense an environment, such as human, traffic, and signal. Most of our customers use AI to develop their perception algorithm. And after a perception, an AV ADAS controller will have to make a decision about how to drive the car. How much throttle per pedal should I brake? How much should I turn? All of these would be decided by AV ADAS controller. So this is the video of a camera. And LiDAR and high-definition map are also used in advanced autonomous vehicles. LiDAR can have more outline details than camera and radar. Developers also use it to do the navigation and the localization. Radar is used in AV ADAS since the technology of radar and controller is developed for decades. Unlike radar and LiDAR, camera sensor is required more and more than past 10 years. Let's take a look about what is the customer's need and the key point. Camera, just like our eyes, can help AV ADAS vehicle to see. For AV ADAS developer, they use AI technique to develop the perception algorithm. For this reason, they need not only the camera output image, but also the ground truth camera. As you can see, most of our customers ask about the depth camera and the image segmentation camera. For example, image segmentation camera can help controller to know in this image which part is the object you are interested. Image segmentation also transfers the image from 3D to 2D. Let's simplify the process of AI perception. It means that users can use much easier data to train and test their AV ADAS controller. Let's see more about camera in next slide. Before we start the topic of from characteristic to real rendering, let's watch this video. This video is from Taiwanese highway. As you can see, the white Tesla driving with AV ADAS system directly crashed into a truck which is already rolled over. Tesla's system, in this case, it didn't train about how to recognize a rolled over truck. In the same time, with this high speed, radar couldn't sense the truck near. How can we generate this kind of image to train our AV ADAS controller? Let's see about what we have in real world. In real world, we have lots of light source, camera lens distortion. We will probably get some dirt and noise. All of these will result in the final image we get. And what is the characteristic image? Characteristic image is for ADAS system. The requirement of the image is based on could we get the outline of object? If we can see the outline of front vehicle, the image is good enough. That is how we develop level 1 or even level 2 controller. However, we are getting into level 4 or level 5. The requirement increase. For AV ADAS system, the requirement becomes real-world rendering. The rendering should be as real as possible. Light tracing, high-end GPU, and the GAN engine are used to produce the image. Now we know about the sensor modeling and the simulation. Now take a look on traffic simulation. For traffic simulation, we can classify traffic simulation into two kinds of simulation. The first one is event-based traffic flow simulation. This kind of simulation is usually set for regulation testing, like Euro NCAP, ISO regulation, or something else. Another one is driver model-based traffic simulation. In this simulation, every traffic car has a driver model. The driver model would decide whether speed up or brake. The below video shows how we integrate CarSim with an open source traffic flow simulation tool called Sumo. Okay, and we can move to the localized elements section. One of the most important things when you want to use a virtual reality simulation for AV ADAS is the localized element. We help customers build up localized building like Sheraton Hotel in Taiwan, some high-speed rail station, optical with words. This kind of environment can help customers rebuild their testing scenario. Let's summarize what we have learned from this session. First, we introduce how can we use vehicle model simulation in AV ADAS. Then, we have shown you the three major sensor requirements from our customer. Third, we have learned that a high-resolution camera with real-world rendering is very important to customers. The fourth and fifth one, traffic simulation and the localized elements, give us a reasonable opponent in reasonable sight. In the next section, we will have a short introduction of color, which covered all the parts we have talked about here. So the next section is the basic introduction of color. Color is an open source simulator for autonomous driving research. Basically, color have the all requirements we have mentioned before: vehicle model simulation, sensor simulation, environment, traffic simulation, and localized elements. Color is based on Unreal Engine. Unreal Engine uses C++ and an unique blueprint system, which makes it very powerful for developers. We not only use color, but also integrate color to CarSim and other third-party solutions. Let's watch the release video of color to see what can it have. As you can see, color have a high-quality camera and run simulation in a large-scale map. It also supports traffic simulation with not only Sumo, but also VSync. Lots of high-fidelity models like pedestrian and vehicle is included in color. We can say that color can fulfill AV ADAS testing requirement. Now we have covered the vehicle modeling the requirement from AV ADAS and the introduction of color. The final part would be the introduction of our solution, the autonomous vehicle testing system by CarSim and color. The idea is embedded the CarSim into color. CarSim have a plugin for Unreal Engine, and we could integrate it into color's vehicle object. In the same time, we could use Verse Bridge to integrate color with AutoWare. That help customer a lot. They can easily put their control algorithm with our tool. So let's move on to next video to see how it works. In this video, we can see that AutoWare is controlling the vehicle which is running in color. The color gives it the sensor data and HD map. AutoWare can run with this data and test about control algorithm. Our customer can easily import their vehicle and the testing scenario with color's architecture. If we looked more details, we can see that the camera sensor in this video shows lots of suspension vibration. That is because of CarSim. If you don't have the CarSim's suspension system, you will probably not meet this problem until you test it in real vehicle. Virtual reality with vehicle model help customers solve this problem in very early stage. In conclusion, we help customers build up their vehicle model and do the VMV. We have lots of experience in every scale vehicle. Through the VMV we have mentioned, customer can build a real vehicle in CarSim or TruckSim. In the same time, we have advanced environment for AV ADAS requirement. Customers use our solution to develop the controller. We also help customers import their vehicle model by CarSim to present real testing environment. For AV ADAS, we integrated with Cara to supply all sensor modules you need in simulation. For example, a depth camera, image segmentation, LiDAR, dynamic vision sensor, camera distortion, and radar. Finally, we integrated with AutoWare. We wish our customer can straightly go on development with our solution. We provide a total solution for vehicle modeling, advanced virtual environment, and the controller development environment. Test in our environment will decrease the time and cost of real testing. That's all for today's presentation, and I will start to answer the questions. If you have any questions, please text it in the chat room, and we will answer it.